Hello, this is Mr. Kinyanola, and I'm going to show you the reason for the tangent radius theorem. Is it a theorem? I think so. Yes, it's a theorem because it's proven. So the tangent radius theorem says this. If a tangent line, a tangent line is a tangent line if it only touches the circle at exactly one point. If a tangent line connects to a radius, that tangent line and radius are perpendicular. They make a right angle. So why every time we have a radius that connects to a tangent line at the point of tangency, why do they always make a right angle? Every single time there's another 90. So why are these always 90 degrees? And I'm going to show you why. So in order to understand why each radius is always congruent to the tangent line on a circle, we have to understand perpendicular distance. So perpendicular distance. Perpendicular, if you guys remember, perpendicular means just two lines that make a right angle. So a right angle. So in order to understand the concept of perpendicular distance, let's look at this. So perpendicular distance, that concept just merely tells us that the shortest distance between a line and a point is another line that is perpendicular to that point. So if I take my good old protractor and I line it up with a 90 right there, and I make a right angle like that, I can guarantee you that this is the shortest distance from this point to this line. And we can do that without even using a ruler. We can use some logic. So this line is perpendicular to this. This is the shortest distance. How do I know? Well, if I drew a line like this, I just made a right triangle. And this line right here that I just drew is, do you know what that's called? Yep, the hypotenuse. And the hypotenuse is the longest side in a right triangle. If this is the longest side in a right triangle, then this is shorter. This is the shorter of the two sides. We're not going to compare this because we just really care about this. Is this really the shortest distance between this point and any point on this line? Well, it can't be this because this is the hypotenuse. If I drew a line that was like that, this would still be shorter than this side right here because this is also a hypotenuse in this right triangle. If I went closer like that, it made this right triangle even smaller. Yeah, this line right here got shorter than this line right here, but this line is still longer than this side right here because looking at this right triangle, this is the hypotenuse. So this is the shortest side. Even if I did this one right here, or this one right here, I think you guys get the point. No matter what, and make that a right angle, no matter what, if I drew any other line and measured that line, it would still be longer than this line right here that's perpendicular to this line right here and connects to this point, because this line right here is not a hypotenuse. It's just a leg in a right triangle. All these other lines that we would draw would all be hypotenuses, so which would be longer than this leg in a right triangle. So the perpendicular distance just says that the line that is perpendicular to this line and that point is the shortest distance. So perpendicular distance. So to the question at hand, why is every radius that connects to the point of tangency on a tangent line, why are those two always perpendicular, or why do they always make right angles? Well, here's our radius. If I took my ruler or any straight edge and I drew any other line like this and made a right triangle, this would be a hypotenuse, this would be a leg. this is longer than this side. And if I did that, and if I kept on doing that, any other line would be a hypotenuse. So this right here, the distance from the center to that point of tangency is the shortest distance. And because of that, because this is the shortest distance, according to perpendicular distance theorem, this line right here has to be perpendicular to this line right here, because this is the shortest distance. Not this, because that's a hypotenuse. Not any other line that I draw, because any other line would be a hypotenuse. Not this one and only leg. Alright, so for those of you guys that want a formal proof on this, here's a formal proof, here's a technical proof, the mathematical proof for this. So if I label this point our center O, actually I'm gonna label it C for center. I'm gonna call this point right here A. I'm going to call this point over here B, and I'm going to call this point right here D. Okay, so we've got CA, which is a radius. We've got CD right here, which is also a radius, and then this extension DB. So first thing in our proof, I'm going to say that CA is congruent to CD because of radii, both radii, not radiuses, but radii, the plural. And then we could also say that CB, so CB is equal to CD plus DB. And you could say, if you want a reason, segment addition postulate in our 2-column proof. If we're doing this 2-column proof with a statement and reason, so these two are congruent because of radii. These CB just adds up to equal, well, CB is equal to CD plus DB because we're just adding segments to make a full segment. And because of that, so this, we can say that CB is greater than CA, because CB is DB plus CA. So thus, because CB is greater than CA, and CB is anything, any line from the center here. So because of that, CA has to be perpendicular to AB. And if you want a reason, you can say perpendicular distance, because CA is the shortest distance from the center to here compared to any other line. All right, so there you go. There's your formal proof of why every tangent line is perpendicular to the radius that meets it, using, where's that piece of paper, if I could find it. I can't find it. Well, using the perpendicular distance theorem. All right, hopefully that makes sense. Hopefully you got one step closer to being better at geometry. All right, and yeah, so if you guys have any questions, if you guys want me to make any other video on geometry, feel free to let me know, message me. This one was made because of a request earlier. So have a great day.